Okay, welcome to the screencast of how to solve problems that are using gravitational potential energy and kinetic energy to find a roller coaster rider's potential energy, kinetic energy, and velocity at any point along a roller coaster track. The first thing we need to know when we start is that the total energy that our rider is going to have is always going to stay the same. Total energy will always stay the same, and that total energy will always be equal to the potential energy that that rider has plus the kinetic energy that that rider has at any point in time. So the total energy will stay the same, but the amount of potential energy might go up and down as the kinetic energy goes up and down. But overall, those two need to add up together to equal the total energy that the rider has. Let's start at the top of the roller coaster. We see that the rider's velocity is 0. We see that his height is 80 meters and has a mass of 60 kilograms. First, I'd like to calculate the potential energy of this rider. I know that because he's on a roller coaster, there's no motor or elastic bands or anything else giving potential stored energy. The only thing storing energy for this rider is the rider's height and its potential to fall, which is its gravitational potential energy. And I have a formula for that. I can actually calculate the exact amount of energy in that potential using this formula: mass times the acceleration of gravity times height. And that will equal my gravitational potential energy at point A. I just plug some numbers in now. I know that this rider is 60 kilograms. I got that from the problem here. I know that the gravitational acceleration of Earth is always the same. It's 9.8 meters per second. And I see that the rider's height is 80 meters. I plug those into a calculator, and I should get 47,040, and then I'm talking about energy, and the unit of energy is always joules. So that's going to be my potential energy at point A, because there is no other source of potential energy here. It's just the gravitational potential to fall and ride down the track there. Next, I use a little logic, and I think about what kinetic energy is. Kinetic energy is the energy of motion, and the rider at the start really isn't moving at all. They have a velocity of 0. That should be a little v there. If I put in a 0 for velocity in this equation here, my kinetic energy, of course, once I multiply out, is just going to be 0 joules of kinetic energy at the very start. And then we know the velocity already. The velocity of that rider, it's told us, is 0, and the units is meters per second for velocity. Now things are going to start to get a little bit trickier. What we're going to have to do is start to think about what the rider's potential and kinetic energy will be at some different points in the graph. We're going to start now on point B, which is right here at the very bottom, and I see that that is right flat on the ground, and so the rider's height at this point would be 0. The first thing I'd like to do is calculate the potential energy the rider has at point B, and the gravitational potential energy formula, of course, is mass times gravity times height. The rider's mass is 60 kilograms. Gravitational acceleration is still the same. It's still 9.8. And the height here is 0. When I multiply 60 times 9.8 times 0, I find that there is no gravitational potential energy left. It's 0 joules. So we end up with 0 joules there. Now, however, I'm going to calculate the amount of kinetic energy at that point. And to do that, I'm going to use this equation up over here. Total energy is equal to the potential energy of the rider plus the kinetic energy. If I look back at point A, I see that we had 47,040 joules, and we had no joules of kinetic energy. So the total energy available to this rider was only here in this potential energy of how high up the rider started at. So I want to know the total energy here. I fill in the amount for potential energy, 47,040 joules, plus at the starting point here there was no kinetic energy. So total energy must be 47,040. Total energy equals 47,040 joules. Well, now at point B I need to find out how much kinetic energy there must be. The rider has ridden all the way down to the track to the very bottom. They have no more potential energy, and I think about that law of conservation of energy. Can I create energy or destroy energy? No. I can only turn it from one form into another. I have no more potential energy left, so I must be only kinetic energy at this point. So that means I have 47,040 joules of kinetic energy at the bottom of this track. Pretty cool. Now here's where it gets a little bit fascinating. I have a formula for kinetic energy. I know through this formula how velocity and mass are related, and I can see that if I simply plug in my numbers, I can actually calculate the exact velocity of that roller coaster just by knowing how high of a drop it came down. The way I'm going to do that is by putting the numbers into this equation. So my kinetic energy is 47,040 joules, and that equals 1/2 times the mass, and here's my mass, times 60 kilograms, times velocity squared. Now I just do some algebra here, or some arithmetic. I have 1/2 times 60, that of course equals 30, we still have times v squared, and I'm going to bring down 47,040. Now I'm trying to solve for this v, so I'll divide out the 30 on both sides. These 30s will cancel, and I will end up with, I'm just going to bring everything right up here to the top. I end up with 1,568 equals v squared. Now I'm almost there. I want to find out the velocity, not the velocity squared. So to get rid of this little square, I need to do a square root. Those will cancel then. If I do that to one side, I got to do it to the other. And I end up with 39.5 equals velocity. And my units, of course, are going to be 35.9 meters per second because I'm in a velocity. Okay, wow. I just actually calculated the velocity of a roller coaster if the roller coaster's first hill is 80 meters tall. And that's going to be true no matter what the shape of that fall is. That roller coaster will convert all of its potential energy into kinetic energy by the bottom of the roller coaster and be traveling at that speed. Very cool. Now it's time to calculate point C, and this is where things can maybe get a little more difficult. At point C, I see that the roller coaster has gone down the hill, turned all of its potential energy into kinetic energy, but has now come back up the hill and gained some potential energy in exchange for losing some speed, which would mean losing some kinetic energy. We can still calculate the velocity of that roller coaster at point C because we know the total energy in the system. And we know that the total energy has to equal the potential energy plus the kinetic energy. So watch what I do. I'm going to first calculate the potential energy coming from this climb. So I'm going to figure out how much potential energy the roller coaster gained as it climbed back up. Our formula for that is pretty simple. It's gravitational potential energy. That's the potential energy from climbing up the hill is equal to the mass times the gravity times however high up it is. Our mass is still 60 kilograms. Gravitational acceleration is always 9.8 on Earth. And the height here, we see that it climbed up 35 meters. I'm going to plug those into my calculator, and I'm going to get that the gravitational potential energy, or just the potential energy, because that's the only form of potential energy we have in this roller coaster, is 20,580 joules. So at point C, that roller coaster has climbed up and gained back 20,580 joules of energy. Now I look at this total energy idea and I say, well, the roller coaster started off with 47,040 joules of energy. It converted them all to kinetic energy, and then it took some of that speed energy, some of the motion energy, and lost it as it climbed up the hill. It began to go slower as it climbed up the hill, turning that energy into potential energy. I can use this relationship, the fact that the total energy equals the potential energy plus the kinetic energy. I already know the total energy available. What was the total energy that this roller coaster started off with? Well, it was 47,040 joules. And I also know the potential energy at point C. I know the potential energy that the roller coaster has gained back. It has gained back 20,580 joules. And according to my total energy equation, whatever's left over has to be made up by the kinetic energy. So now I just do a little quick algebra here, and I say 47,040, and I subtract out this 20,580 to get it out of the way here. 20,580. So then I know, and I'm going to write it right here, that the kinetic energy must equal... Oh, why don't you pause and go find out what it equals? Okay, now that you're back, we know the kinetic energy. After we subtract the potential energy out, whatever's left is all kinetic energy at this point. And we have 26,460 joules of kinetic energy in the roller coaster left over at point C. I'm going to now put that into my box here, 26,460 joules. So I see this roller coaster had all potential energy, converted all of it into kinetic energy at the bottom. All of its energy is in motion, and then as it climbs back up, it's storing some of that energy again in that gravitational potential energy by climbing higher, and it slowed its speed down. And using this relationship of total energy, I found that the kinetic energy was 26,460. Now it's asking me to calculate, okay, well, what's the velocity of that roller coaster at point C? And now comes again the beauty of that kinetic energy equation. I know the kinetic energy, and I know what makes kinetic energy. It's 1/2 times the mass of that object times its velocity squared. So I fill it in the equation. I say, well, I know that there's 26,460 joules at point C. That's how much potential energy it's gained, and that's got to be equal to 1/2 times the mass, and our mass was 60 kilograms, times the velocity squared. Now we're just going to try to solve for velocity squared using algebra steps. I do 1/2 times 60, I get 30. Got to bring that v squared down. And I still have to bring down the 26,460 joules. Trying to get v by itself, so I divide out this 30 from both sides. And I get, what do I get? I get 882 equals the velocity squared. But am I done? Of course not. I need to square root both sides to get rid of this square. And that gives me a velocity of 29.7 meters per second. I really should have rounded this one up too. This is now the velocity found from the kinetic energy that was found by using the potential energy of how high it had climbed up, subtracted out of the total energy in the system. Thanks for listening, everyone. Now it's your job to go down to the bottom here and to use the same roller coaster. It's the same heights on the roller coaster, but now we have a different passenger. The mass is 120 kilograms. And I want you to calculate the potential energy, kinetic energy, and velocity of that rider and roller coaster at every point. If you have questions, go back and follow through on my examples again and look back at your work. And I look forward to seeing you with these finished on Tuesday. Again, really try to work hard at this one because there's going to be test questions like this, and they tend to be the more difficult test questions on the test. Thanks. Have a great weekend.